Hi class, today we're continuing our introduction into thermodynamics, and we have moved beyond heat capacity and specific heat, and for all of these examples that we've used so far, we've been talking about heat flowing and kilojoules of heat, and those are measured values using a calorimeter. That's a device that's used to measure the heat involved in a chemical reaction or physical process as it's transferred from the system, the substance or the reaction, to the surroundings, which would be the measuring apparatus. So everything is all about heat flow. Under ideal circumstances, the net heat change is zero due to the conservation of energy. So the heat of the system and the heat of the surroundings should be equal to zero. Now, in the textbook, the sign negative is to show that the two components are opposite in the direction of heat flow, and we can actually be a little bit more specific about it. So our Q, our heat flow of our system, is also going to be our reaction for our chemical reactions. And if it's got a negative sign, that means that Q surroundings is positive, and it is exothermic, as the reaction is losing heat, otherwise known as producing heat, as a product. If the Q system is positive, that means that we have an endothermic reaction or endothermic process, and while the surroundings are losing heat into the reaction. So that would be endothermic. In example 4, we show a exothermic process where we have a 360 gram piece of iron that's dropped into water at 24 degrees Celsius. The final temperature of the water is measured to be about 42 degrees Celsius. Calculate the initial temperature of the iron. So this is a hot piece of iron being dropped into water. So the surroundings in this case is the water, and that temperature is going up. The iron is the system, and that temperature is going down, meaning that it is an exothermic process. This is not a chemical reaction, this is just a process where you have a piece of iron losing heat. So we have a negative Q system as heat is flowing out of the system. So the Q of iron is negative, and the Q of the water is positive. And from earlier, Q is equal to the specific heat times mass times change in temperature. So we have negative Cm delta T for iron is equal to Q of water, which is Cm delta T for water. We can look up the specific heat of iron in a provided table, where we have iron shown here, solid, has a specific heat of 0.449 joules per gram Celsius. So we can take that value and plug it in for our specific heat of iron, which is 0.449. Multiply that by 360 grams of iron, multiplying that by the change in temperature, which is our final minus initial, so we have 42.7 degrees minus our T initial. Similarly, over to the right, we have our Q for water, which is Cm delta T, and we use the specific heat for water, again from the same table provided, which is 4.184 joules per gram Celsius, multiplied by 425 grams times the change in temperature, 42.7 Celsius minus 24.0 Celsius. On the left side of our equation, that gives us negative 161.64 joules per Celsius times the difference, which is equal to 33,252.3 joules. That is our Q surroundings. We have, if we do some more math out on the left, we have negative 6,902.02 joules minus our negative 161.64 joules per Celsius times our T initial. And if we do some math out by subtracting the joules from both sides and then dividing by our joules per Celsius, we are left with a T initial of 248 Celsius. So instead of a physical process, we can apply the heat flow to a chemical reaction, where we have 100 milliliters of 0.2 molar sodium chloride aqueous reacting with 0.2 molar silver nitrate aqueous, both at 21.9 degrees Celsius in a calorimeter. The temperature increases to 23.5 degrees Celsius as solid silver chloride forms. How much heat is produced by this reaction? So the first thing that we need to do is write out the chemical reaction. We are given 3 out of the 4 compounds. We have sodium chloride aqueous, silver nitrate aqueous, and the precipitation of silver chloride solid, all given to us in the problem. we can figure that sodium is going to be a +1 ion and calcium is going to be a -1 ion, giving us a -1 ion on chloride and a +1 ion on silver in the product. That would lead us to believe that unless a redox reaction happens, that silver has got to be +1, and the Lewis structure would confirm that nitrate is -1. And that gives us sodium nitrate, and that's nice and charged, balanced, so we don't have to do anything else. Our negative Q reaction is going to be equal to positive Q solution as the temperature in the solution is increasing. So heat is flowing out of the reaction into the solution, and that could give us heat as a product. So negative Q reaction is going to be equal to MC delta T. So we need a few of these terms. First, we need the mass of water. The Q solution, which is the water. So our volume of water we can actually get from the problem because we are mixing two solutions that both have a volume of 100 milliliters. Those are both aqueous solutions, so we kind of hidden in the problem is the fact that we are starting with 200 milliliters of water. So that's going to be an important thing to be able to find. So we have 200 milliliters of water of total solution based on a 1 gram per milliliter density of water. That gives us 200 grams of water. From our specific heat table, we have 4.14 joules per gram Celsius as the specific heat of water, and our delta T for our solution is going to be final minus initial, which is given to us for water. So our final temperature is the heat at which it increased to, so we have 23.5 degrees Celsius minus the initial, which is 21.9, giving us a difference of 1.6. Our Q reaction is going to be equal then to 200 grams times 4.184 joules per gram Celsius times the difference in temperature. So our Q reaction is going to be equal to negative Q reaction is equal to 1,338 joules or 1.34 kilojoules. So 1.34 kilojoules, this is how much energy has been released by the reaction. We're going to move on now and do a little bit of a deeper dive into enthalpy. And that requires us to first talk again about internal energy. So all of the total types of energy possible in a substance is called its internal energy. And delta U is equal to the final internal energy minus the initial. Delta U is also equal to heat flow plus work. As the system undergoes change, its internal energy can also change, and that is usually in the form of heat transfer. As we've seen, negative Q system is going to be an exothermic reaction. A positive Q system is an endothermic reaction. I had previously intended to do a little bit more of an explanation about work, but that's not going to come up again, so I've decided to skip it. Enthalpy is the total heat content of a system, and that's related to internal energy, which is related to also pressure and volume. So we can see that enthalpy is equal to internal energy plus the product of pressure and volume. The change in enthalpy at constant pressure is what we're going to be very, very interested in. So this is going to be delta H. So delta H is going to be equal to delta U plus P delta V. P does not have a delta in front of it because we're at constant pressure. Delta V, when it's positive, that's an expansion. That is the change in volume getting larger, so that's an expanding system. In that situation, work would be negative. Delta V being negative, that's a compression. That is your volume getting smaller. That situation has a positive work because you have to do work on the system in order to shrink it down. Let's see how our delta H, change in enthalpy rather, can be applied to a system that is a reaction. So the chemical combustion of hydrogen gas and oxygen gas shows that when 1 mole of H2 and half a mole of oxygen react to form liquid water, 286 kilojoules of heat energy are released to the surroundings. So we would write the equation out with our phases, so gas, gas, and liquid, and delta H is negative 286 kilojoules. Delta H is an extensive property, which means that it depends on the amount of water. This is very similar to the difference between heat capacity and specific heat. So heat capacity is also an extensive property, and that depends on the amount. So if delta H for the equation is doubled, the change in energy also has to be doubled. So if we were to get rid of the non-integer, the half coefficient of oxygen, we could multiply everything by 2, and we would get 2H2 plus O2 yields 2H2O. And if we did that, we would have to multiply the change in enthalpy by 2. So we would overall actually be losing 572 kilojoules of heat energy. I read this negative 572 like this. That is 572 kilojoules that's being released per the reaction. What I mean by that is that's 572 kilojoules that's released for every 2 moles of hydrogen gas that's consumed. That's also 572 kilojoules of energy that's released for every 1 mole of oxygen. So sometimes it gets a little confusing as to where you multiply by 2 and where not. Here you don't need to. So delta H when it's negative is exothermic, when it's positive it is endothermic. In example 8a, we have a situation where 1.34 grams of zinc solid is reacting with 60 mils of 0.750 molar HCl. 3.14 kilojoules of heat are produced. In this reaction, zinc is the limiting reagent. Determine the enthalpy change for the reaction. So we're going to do everything in terms of moles of zinc because moles of zinc are the limiting reagent. And when we do that, we figure out that we have 1.34 grams of zinc multiplied by 1 over the molecular weight of zinc, giving us 0.0205 moles of zinc. We can then figure out how many kilojoules of heat are released for every 1 mole of zinc. And when we do that, we can actually discover what the change in enthalpy is for this reaction, and then apply it to any other situation where we have any amount of zinc or any amount of hydrochloric acid. So delta H is going to be equal to 1 mole of zinc times negative 3.14 kilojoules for every 0.0205 moles of zinc. The moles of zinc cancel, and we're left with a total of negative 153 kilojoules. So that becomes our delta H for this reaction, which I would consider sort of like our universal release of energy for this reaction. And we can also take a look at what it is for every 2 moles of hydrochloric acid based on the balanced equation and prove that it should be the same. In order to do that, we need moles of hydrochloric acid. Zinc is the limiting reagent, so we have to sort of do that based on zinc. So 0.0205 moles of zinc, we can multiply by the stoichiometry of the reaction. 2 moles of hydrochloric acid react for every 1 mole of zinc, and that leads us to a situation where we discover that 0.041 moles of hydrochloric acid are reacting. So the delta H is going to be equal to 2 moles of hydrochloric acid per the reaction, multiplied by negative 3.14 kilojoules for every 0.041. And that leads us back to, again, negative 153 kilojoules. And that is showing that 153 kilojoules of energy are released for every 1 mole of zinc and for every 2 moles of hydrochloric acid. That is where we're ending today on Friday. And that will also be the end of the material for the exam. We do not have a problem set that covers up to our introduction to thermodynamics and enthalpy, so that will be pretty light on the exam.